Okay, let's do the probability bounds. Sometimes also called probability inequalities. We start by the Markov bound, which is for non-negative x. So the probability that x greater than or equal to a is less than or equal to the expected value of x over a. Chebyshev bound. It tells that for a random variable with expectation m and variance sigma squared, the probability that the absolute value of x minus sum a minus m, greater than or equal to sum a is less than or equal to sigma squared over a squared. And finally, the Chernoff bound, which tells that the probability that x is greater than or equal to a less than or equal to e to the minus sa times the expectation of e to the s x. Okay, as we can see here, these are probability inequalities or probability bounds that in cases where you have a very advanced PDF, a very advanced PMF, they can tell you something. They can tell you a piece of information about your probability. They bound your probability from above. They tell you that your probability is less than or equal to this bound. These three different bounds, they use different sets of parameters. So the information they convey is quite different from each other. And the accuracy of each of these bounds really does vary. And we will see examples on that. All right? So we will try to prove one of them. Let's try to prove the Markov bound. The expected value of x in the continuous case is the integration x equals 0 to infinity. Remember that x is non-negative, okay? X fx of x dx. We will separate this integral from 0 to a x fx of x dx plus the integral from a to infinity x fx of x dx. X is non-negative. Probability density is non-negative. So when we skip a term, this expectation becomes greater than or equal to the integral from x equals a to infinity x fx of x dx. And then I'm going to be writing something here from x equals a to infinity a fx of x dx. I just removed x, replaced it with a. What should we put here? Greater than or equal to, less than or equal to, equals to. Greater than or equal to, why?
Because integration goes from a to infinity, so x is greater or equal to a.
Exactly. We took essentially the lower bound of all the possible values of x, and we just did it here. So thus this thing is also greater than or equal to x. This is the probability you are seeking, x greater than or equal to a, and thus this proves the inequality, right? Okay? Awesome. Let's give examples. Example 1. These examples are targeting the evaluation of the quality of the bounds. I am not much interested in you making some substitutions, and that's not what I want you to do. Let's evaluate the quality of these bounds, okay? All right, compare the Markov bound with the exact probability for the event x greater than c as a function of c 4x binomial with p equals 0.5 and n equals 10. All right, the question is clear, right? So we just want to compare the Markov bound with the exact probability for a particular event. We want to see what the bound will give us for the event. We want to see what is the exact probability of this event for a particular random variable that is binomial with these characteristics. All right? So the bound, the Markov bound, tells that the probability x greater than or equal to c less than or equal to the expected value of x over c. What is the expected value of x? Let's work with symbols for now. We will substitute numbers at the end. What is the expected value of x? Yeah, binomial with n and p. Expected value is np, right? np over c. So, is this the probability we are seeking? Is this the probability we are seeking? It's a probability x greater than or equal to c. We are seeking x greater than c. Are they the same? This is a discrete random variable, so they are not the same, right? So this thing is the probability that x greater than or equal to c minus the probability that x equals c. From the bound immediately less than or equal to np over c minus this particular probability, which is a binomial probability, n choose p, p to the c, 1 minus p to the n minus c. What is the exact probability? It is the probability that x greater than c. In general, when you have the probability that you have an event greater than a specific value, it is tricky because not every single time you will have an infinite summation that converges. Not particularly going to be the case. So sometimes it is easier to do a trick with this probability. What is this trick? Thank you. 1 minus the probability x less than or equal to c. And in this case, it will be 1 minus the summation from k equals 0 to c, n choose k, p to the k, 1 minus p to the n minus k. All right. We want to quantify, we want to evaluate the bound in comparison with the exact probability. We will try to put them in front of each other for p equals 0.5. We will have n over 2c from the bound minus n choose c 0.5 to the n. This will become 0.5 to the n, this will become 0.5 to the n, right? It's 0.5 after all. This is greater than or equal to. We have this term, which is 1 minus summation from k equals 0 to c, n choose k, 0.5 to the n. Let's just take this term here for the sake of simplification. N over 2c greater than or equal to 1 minus summation from k equals 0 to c minus 1, n choose k, 0.5 to the n. Let's make the evaluation right now for n equals 10, and we will do only two cases for c equals 1 and c equals 10. For c equals 1, we have n equals 10, so this left-hand side will become 5, and the right-hand side will become some probability. Okay, wow. Let's stop in front of this a little bit. The left-hand side is 5. So the bound is giving us some probabilities less than 5. Yeah, of course. Probability would be less than 4. That's an awful bound. So the left-hand side is giving us 5. This tells how mediocre the Markov bound could be. Let's do the case of c equals 10. The left-hand side in this case becomes 0.5, And at the moment you become optimistic, oh, this could be some probability. Okay, let's try to do the right-hand side. Can someone immediately tell me what the right-hand side would be? If you are taking all the terms without an exception, what will this summation be? Yeah, exactly right. You are summing over a PMF, taking all its values, right? Now we took one out of it, and it's 1 minus. So it's the only term that remains, right? The only term that remains is 0.52. Okay? So only when you started to think it can give you some relatively meaningful bound, you realize that the probability is much smaller. Orders of magnitude smaller. So this tells us why this bound, this tells us that this bound is not too good. Any idea why this bound is not so good? What's up? I'm just asking, any idea why this bound, the Markov bound, is doing so bad? In the end, the quality of a bound will rely solely on the parameters, the ingredients in the bound, right? You give the bound some parameters, it will give you something useful or not. It depends on the parameters. What is the only parameter related to the random variable that is part of the Markov bound? Expectation tells nothing about randomness. It just tells you the expected value. Even the expected value of a constant is non-zero. Expectation tells nothing about randomness. So this is why this bound is really not too good, because it relies only on one parameter, being the expectation. All right, let's qualify another bound with an example, which is the Chebyshev bound. Let X be the number of successes in n Bernoulli trials where P success is P. Let Y equals X over N, P the average. Apply Chebyshev bound for this event Y minus P is greater than A. Bless you. And check what happens as n goes to infinity. All right. So again, what is the Chebyshev bound telling us? It is telling us that the probability X minus the mean M greater than or equal to A, right, is less than or equal to sigma squared over A squared. That is what the bound is telling us. We want to reach here from here. So let's look at this. We have A, we have greater than versus greater than or equal. We have P versus M. Okay? So let's first get M, which is My, which is expected value of Y, which is 1 over N expected value of X. What is the expected value of X? X is their sum. So 1 Bernoulli is P. So the sum will be? What is the sum of independent Bernoullis? Yeah, so the sum of independent Bernoullis is a binomial, right? Right? So it's 1 over N, NP, which is P. Ha, good. So now we can put P here. The only thing that remains is the greater than or equal. Okay, but let's first do the sigma squared is sigma y squared is the variance of y is 1 over n squared v of x, which is p 1 minus p over n, because remember that you have here x being the sum over independent Bernoullis. All right, great. So the probability we are seeking is the probability that x minus m is the probability that x minus p is greater than a. But lucky for us, this probability is already going to be less than the probability that x minus p is greater than or equal to a, because you added another value, another non-zero, non-negative probability, right? And the bound is immediately telling us that this becomes less than or equal to this guy, p 1 minus p over n a squared. All right, good. Because this one is less than or equal to sigma squared over a squared. Great. What happens as n goes to infinity? Exactly. Probability can never be negative. So when you say something is converging to something that is 0 or less, it is 0, right? Thus, the probability of absolute value x minus p greater than a goes to 0. Okay. Okay. What does that mean? What does this thing mean? Probability absolute value of x minus p greater than arbitrary positive entity is converging to 0. What does that mean? What does that tell about x? Yeah. Yeah, exactly. This means that x converges to p. Okay. We will talk about this stuff later, but let's discuss it in brief right now. What is the fundamental idea of parameter estimation? Parameter estimation is a process in which you have a random variable. That random variable, there are some parameters about it you don't know. Its mean, its variance, maybe one parameter about its PDF. There is one parameter about your random variable that you don't know. But you have the ability to keep sampling this random variable, to keep creating independent, identically distributed versions of this random variable, and apply a function to them, and from that function, you try to estimate the missing parameter, all right? So a parameter is missing, but you can sample and create IIDs, and then you apply a function to these IIDs, and from that, you try to understand, you try to realize, you try to reach the missing parameter. What we did here is essentially sort of parameter estimation, and we will link it to the Chebyshev inequality in a few minutes. What did we do here? We have a Bernoulli random variable. That Bernoulli random variable, we don't know its expectation. And its expectation is p, which is a parameter in its distribution too. So we decided to make an estimator. That estimator is, let's try to write it here. That estimator is theta, and that theta is essentially what we did here. 1 over n summation I equals 1 to n bi. Okay? It can be written also as theta of b1, b2, dot, 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 up to bn. All right. That estimator, the Chebyshev inequality, told us that as n goes to infinity, as we take more and more and more and more samples and average, that estimator will end up giving us B. So limit as n goes to infinity, theta, let's call it theta n, equals P. Is P the expectation of BI? Yes. So this is a good estimator. This estimator is good. Averaging, which is something we will see later on, by the law of large numbers, is actually as n goes to infinity for IID random variable, gives you the expectation. Okay, but now what is this telling about the Chebyshev inequality? It's a good inequality, it's a good bound. It told us something. It actually told us that this theta will go to B. It told us that this variable we invented, which is y here, that I call the theta here for the sake of just using a symbol for estimation, is actually converging to P as n goes to infinity. Why is the Chebyshev inequality better than the Markov inequality? What do you think? What's up? Exactly. In fact, both, right? The mean and the variance, right? It is because the Chebyshev inequality, in its ingredients, it has the mean and the variance. All right? Okay. Any questions? Because now we will move on to something different. Recursion. What is the goal of recursion? Find the probability P as function of itself. Find the expectation E as a function of itself, and avoid searching for underlying distributions. Okay. Now we are on our way to become more dangerous. So what are we doing here? We will be introducing some ideas to get to the probability of certain events without even searching for underlying distributions. To get to the expectation of certain events without even looking for underlying distributions. Recursion exists around you in many, many, many ways. In fact, you did write some software programs already, and you have already seen some recursive formulas. Now, today, we will try to show how it works in probability. All right? So let me ask you a question first. All of you have the lecture notes one way or another with you? Right? Okay. So I don't need to write the entire problem. So you have a man playing chess versus online program. He loses with probability P, wins with 1 minus p. And p is fixed. When he wins, the score increases or decreases by 1 if he wins, loses. And he starts at a score of 0. Plays indefinitely, but gets blocked. If his score drops below 1. Drops below 0, sorry, less than or equal to minus 1. What are we searching for? We are searching for the probability that the man gets blocked. So is the problem setup clear? So you have a man playing chess versus an online program at certain difficulty level. You know, sometimes you try to do something, it doesn't work out, you get angry, and when you do it once, you feel like, I'm better than the computer, you try to do it again, and then you fail, and so on and so forth. Probably you did it a lot. But the only trick here is that the computer program will block the man once he gets a score that is below 0, okay? And we want the probability that the man gets blocked, all right? Why are these markers are left here if they are terrible? Okay. So what we are going to try to do here is to see how to express the probability of getting blocked. So the man starts here, score 0, that score minus 1, that score 1, that score 2. From 0, he will lose with probability p, wins with 1 minus p. From here, he can come here with p, 1 minus p, and here with p, here with 1 minus p, and then 1 minus p, 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 1 minus p, dot, 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 dot. All right, we will try to decompose this event into the first order of business, which is essentially that the probability that the man loses first game, and following that, adding the probability that he wins first game, but blocked later. So, what is the probability that the man loses first game? This one is obvious. This one is P. What is the probability that he wins the first game? Awesome. Times the probability that the man gets from 1 to minus 1. This probability can be decomposed into the probability that the man gets from 1 to 0 times the probability that the man gets from 0 to 1. These probabilities are composed of all the possible scenarios of getting from a point to another. These probabilities, this guy and this guy, are not like these probabilities. These are not single-step probabilities. These are more closer to the probability of getting blocked. The probability of getting blocked is the probability of getting blocked in general. Under that scenario of 0 to minus 1, under the scenario of 0, 1, 0, minus 1, or 0, 1, 2, and then going back minus 1, under all the possible scenarios. Okay, what is the relation between these two probabilities and the probability of getting blocked? Let's, for simplicity, call it PB. What is the relation between this one and PB and this one and PB? Let's look at this one first. What is the relation between the probability of getting from 0 to minus 1 and PB? equal 100%, right? That's exactly the problem setup. The man stands here, and you want to look at the probability that collectively he gets to -1. So this guy is PB. How about this guy? What, small p you mean? Who is talking? Please answer. Yes, it is actually PB. And this guy is also PB. Great. Remember that this setup is infinite, right? So when you think about it, if you want to go from here to here in an infinite setup, the events you are going to be facing are the exact same set of events you will face if you want to go from here to here. And the exact same set of events you will face if you want to go from here to here. And the exact same set of events you will face if you want to go from here to here. This process is stationary and infinite. Remember that. If this process is finite, the answer PB would have been wrong. But this process is infinite, and you are looking at all the possible events to collectively get from a point to another. Let's think about them. To get from here to here, you can go in 1 step, you can go in 3 steps, you can go in 5 steps, but what is the difference? That's exactly what you will face to get from here to here. Right? Good? And thus, PB equals P plus 1 minus P, PB squared. We didn't search for any underlying distribution. It's just we expressed PB in terms of its own self. That is the recursion we were looking for. How to solve this thing? Quadratic equation, right? So PB is 1 plus or minus square root 1 minus 4, 1 minus P times P over 2, 1 minus P. And this thing becomes either one of 2 cases. It is either PB equals 1 or PB equals P over 1 minus P. Because what is underlying this root will end up itself being 1 minus 2P. Everybody's fine until now. Okay? Can someone tell me the threshold? What is the threshold? When will PB be 1? When will PB be P over 1 minus P? Go ahead.
I did not understand how we say PB to this 1 to 0 and 0 to minus 1.
Great. So let's think about the sub-events leading you to the final event. Okay? To go from 0 to minus 1, what are the possible scenarios? You take it in 1 step, right? Or you take it in 3 steps, right? Or you take it in 5 steps, or you take it in some step in between, okay? Let's look at the set of events leading to going from 1 to 0. It's also you take it in 1 step, or you take it in 3, or you take it in 5, or you play with this zigzag thing. It's the exact same set of events. It will never change. Because this is a stationary process that is infinite. It is called the one-dimensional random walk. It is a stationary process that is infinite. So the set of events leading you to take 1 step from 0 to minus 1 is the same set taking you from 1 to 0, with the exception of the position. The same set from 2 to 1, the same set from 3 to 2, it doesn't change. Okay? Can someone tell me what is the threshold for small p such that we pick this one or pick this one? What's up? 1 over 2, it's a half, but why? That's correct, by the way, but why?
Otherwise it will be greater.
Exactly. So the easy way is to look at this guy immediately and say you want p over 1 minus p to be less than 1, p less than 1 minus p, which tells that p is less than a half. So this is for p greater than a half. This is for p less than or equal to a half. And for the scenario we have in hand, PP at small p equals 1/4 will be 1/4 over 3/4, which is 1/3. Okay. Yeah.
I understand that the same as well, but I do not understand why they are equal to P block.
Why these two are equal?
To P block itself. Didn't you say that?
Oh yeah. So you understand why this equals this, but you don't understand why both are PB. Because the probability of going from 0 to -1 is exactly the probability of getting blocked, right? Because what is the setup of the problem? The setup of the problem was that the man starts at 0. And he will get blocked when he gets to -1. So the probability that he gets blocked is the probability of getting from 0 to -1. That is the exact setup of the problem, right? He starts at score 0. This one, we didn't do much. It's just that's how the problem works. You want the probability that he gets blocked starting from 0, right? Okay, one last thing before we move to our last example. What is this branch telling us? PB equals 1 for P greater than half. What is this telling us? Exactly. So if that man is not good at the chess game, and the probability that he loses is greater than the probability he wins, it doesn't matter when, he will eventually get blocked. This is something certain. All right? Okay. The last example we will do today, example 4. Find the expected number of fair coin tosses needed to get 3 successive tails. So the solution of this problem, here we were talking about an example where P is f of P. This example will be E being f of E. So the event of tail, 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 we will write it as follows. Summation over I, the expectation of tail, tail, tail given AI, times the probability of AI. You definitely have seen this before, right? But it also correlates to something we did together this class, right? What is it? Thank you so much, yeah. So this is the total expectation that correlates to the total probability theorem. It's the exact same logic, and we will do it later on again together. So all what we are trying to do here is just decompose the set of events AI and look at how recursion works. You get tail or head, you get tail or head, you get tail or head. The probability is half, 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 half. Okay. What happens when you come here? What happens to your procedure? Oh yeah. So this is the repeat point. And same as this, and same as this. These points mean repeat. Means nothing. I mean, you got some tails, okay, good for you, and then you got a head, bad for you, repeat. Okay? Great. So let's try to write a recursive formula using the total expectation theorem for this particular set of events. And let's start with, let's call them 1, 2, 3, 4. It is now clear to you why I never completed the tree, right? Because a head at any stage means repeat, return again. That's the completion, okay? So let's start with the simplest event. We will do 4 first. 4, 3, 2, 1. For 4, what is the conditional expectation and what is the probability? What is the conditional expectation for that case? No, 3, right? The probability is 1/8 and the conditional expectation is 3. You are a lucky man. You got the 3 immediately. Life is good. No, let's reverse these. What is the probability here? 1/2. Here, right? Everything is good. What is the function of E we should write here? Let's think together about what happens. Once you get to the repeat stage, what are you waiting for to get the TTT? E, right? You just return it to AI. It's E, okay? But is it only E for this entire branch? Thank you, yeah. Yeah. Because the one you tried is wasted away. So it's the one you wasted and E. Here, it's the 2 you wasted and E. Here, it is the 3 you wasted and E. Right? Clear? So this thing is E plus 1, this thing is E plus 2, and this one is E plus 3, and thus E, you can solve for it, and you will end up having it being 40. Okay? Once again, how could we get these 3 recursive components? Once you get to a head, you repeat, you return to AI. So once you get here, you return to AI. Once you return, you are waiting for E to happen. You are repeating your experiment from scratch. From here, repeat from scratch. So you got E, and the same here you got E, and the same here you got E, but you have also the trials you wasted. Here, it's 1 trial. Here, 2 trials. Here, 3 trials. Observe that what is common between these 2 problems is that we never searched for a PMF to get a probability from it. We never searched for a PMF to get an expectation from it. All right? Okay, so that's the end of our lecture today. You have the homework posted. If you have any questions, as I said, pass by in the office hours or send emails or write to the forum. And I will see you on Thursday.